Okay, so let us continue on. If we look at number 8, the function is 1 over 1 minus x squared. We know that later on a lot of math and science is about form, so later on we're going to change the form, but let's hold on for that for right now. First thing we do is say, look, where's the domain? So the domain of this function, we're either worried about stuff divided by 0 or the square root of a negative. In this case, since we have a fraction, we're going to set the denominator equal to 0. We get 1 minus x squared equals 0. 1 is equal to x squared, which means x is equal to plus or minus 1. That's two places where the function is undefined there, and we're going to use those points when we partition later. So no matter what happens, those are going to be vertical asymptotes, right? And so at those vertical asymptotes, we're going to make sure and partition. So if we look at what we got stuff over here, a vertical asymptote, stuff, a vertical asymptote, stuff. So this would be our domain. Negative infinity to negative 1, negative 1 to 1, and 1 to infinity. Okay. After domain, we worry about the intercepts. So we say the x-intercept is where y equals 0, and the y-intercept is where x equals 0. So setting y equal to 0 here is y. If we set it equal to 0, then the only way that that can happen is if the numerator equals 0, but that can never happen. So that happens nowhere. Then y-intercept is where x equals 0. So if we take our y and set x equal to 0, we see that we get 1, which means 0, 1 is an intercept. Now we're ready for symmetry. And remember, we do that by plugging in negative x into our function. If you end up getting f of x, then your function is even. If you get negative f of x, your function is odd. Even means symmetry with respect to the y-axis, and odd means symmetry with respect to the origin. So we take our function and we plug in negative x. When we do that, we get 1 over 1 minus negative x squared squared. But negative x squared squared is the same as x squared. So this function right here, f of negative x, turns out to be exactly equal to f of x, so f is even, and we have symmetry with respect to the y-axis. In terms of asymptotes, well, for a vertical asymptote, we set the denominator equal to 0, and we get that 1 and negative 1 that we'd gotten earlier. And for a horizontal asymptote, we're wanting to know what happens in the long run. So we take the limit as x goes to positive infinity, and we get 0, because the bottom grows faster than a constant, because it's not growing at all. And we could also go out to negative infinity. Either way, we're going to get the same thing. We're going to get a horizontal asymptote of y equals 0. So now we're ready to talk about increasing and decreasing. And the way that we do that is with this 3-step process. So first, we're going to find the critical values. We're going to partition, and then we're going to chart. So we're going to rewrite our function first. Instead of 1 over 1 minus x squared, we're going to change the form and turn it into stuff raised to a power. So stuff raised to negative 1, that means our form is stuff to the negative 1. So the derivative is going to be negative 1 quantity to the negative second, and then leave the inside alone, but then the inside is negative 2. So negative negative gets a positive 2x on top, and then we're going to put all this on bottom. So it's over this squared. So then we set our derivative equal to 0. Well, that's only going to happen if, for a fraction, if the numerator is equal to 0. And so we get x is equal to 0. And then we only get undefined for a fraction if the denom is equal to 0. So that would mean 1 minus x squared squared is equal to 0. Well, that only happens if 1 minus x squared is 0, which means x is equal to plus or minus 1. And we've already seen those values, right? So we partition step 2. And we have our vertical asymptotes that we spoke about earlier. And then we have this other critical value here at 0. So we've now broken our number line into 1, 2, 3, 4 pieces. Step 3 is to chart, and our chart should look like this. Remember, at any point, if I'm going too fast, you can always pause the video. So in that first interval, maybe we say at x is equal to -2, you get a negative. Let's see. If you put in a -2, you get a negative. And in here, you end up getting a positive. Is that right? You get a positive? No. You would get a negative. But, oh, don't forget, it's this stuff. The denominator is this thing gets squared. So if that's the denominator, then it's easy. It's always positive, yes? Yay. So we have a negative divided by a positive is negative. Here again, if we put in a -1/2, we get a negative divided by a positive is negative. Then something in the interval from 0 to 1. Let me grab this and pull that down a little bit. Something in the interval from 0 to 1, maybe at x is equal to a positive 1/2. We get a positive divided by a positive is positive. And then maybe at x is equal to like 311, we get a positive divided by a positive is positive. So our function is decreasing, increasing, and increasing, right? Okay. So since f prime goes from negative to positive, at x is equal to what value? 0. That means f has a local min there. And remember, that's not a vertical asymptote. The function's actually defined there, so we're good to go. Okay. So we've done that. We don't have any local maxes. That was part F. So part G, how's your lunch, kid? Eleanor. Your lunch is good? Good. Okay. So now let's go over here to concavity. Okay. So for concavity, again, it's going to be the same process. Step 1 is to find the critical values, but this time it's where the second derivative is 0 or the second derivative is undefined. Step 2 is going to be to partition. Step 3 is going to be to chart. All right. So when we look at this function, so let's see what our function was. Remember, we already had the derivative. It's right here. So I hit copy, come down here, and I hit paste. So there's the function that I want to take the derivative of, because that's my first derivative. So my second derivative is going to be low d high minus high d low over low squared. Low squared. So I'm going to take low d high minus high, move this over, times the derivative of low, which that is low, right? So now we just have over low squared. So it's 1 minus x squared. Squared gets squared. So we end up having what? 1 minus x squared times 2 minus 2x. And then this is going to be a chain rule right here, right? Because its form is stuff gets squared. So its derivative is going to be 2 stuff to the first times the derivative of that stuff. So it's going to be 2 stuff to the first times the derivative of the inside is negative 2x. All over 1 minus x squared. Squared gets squared. Yeah, it's a little ridiculous. So that is the second derivative for anyone keeping score at home. So the second derivative is what? 1 minus x squared squared plus, well, let's take this times this times this, and that, 2, 4, 8, right? 8x squared, but it's positive. So positive 8x squared. And this is left over, 1 minus x squared. The bottom just becomes 1 minus x squared to the 4th. Why is that wonderful? Because now you need to recognize the form of the top. It's a chunk plus another chunk, right? So if it's going to simplify, we hope something cancels out, and it does. When you look at those two terms, notice that inside of both of them, there is this 1 minus x squared. So if you pull it out, 1 minus x squared times 2, let's see, I'm sorry, you can actually pull a 2, 1 minus x squared. If I pull a 2, 1 minus x squared, what's left behind is 1 minus x squared. And then 2 times 1 minus x squared. If I pull it out of this, who would be left behind? Well, how about 4x squared? Right. Okay, so that is going to be what we have. And it's all over 1 minus x squared to the 4th. So let's see. Why is that beautiful? Because now notice this is to the 1st. One of these cancels out and leaves a 1 minus x squared cubed on the bottom. On the top, we're left with 2. And what happens in here? That just becomes 1 minus 3x squared. So all of this turns into 1 minus 3x squared. Okay. So now that is our second derivative, right? So if that is our second derivative, then we now have two things to do. Take the second derivative, set it equal to 0, find out where the second derivative is undefined. Second derivative equal to 0, the only way that a fraction can be 0 is if the numerator is equal to 0. So we have this, but where's, oh, don't forget that's not minus, that should be plus, so that's plus.
That wall in the middle of the book.
I know, that wall in the middle of the book. So there's that, right? But when can that ever equal 0? I think it's pretty clear that this can never equal 0, so it's never. And then undefined for a fraction is going to be where the denominator is equal to 0. So we get this equals 0. If you take the cube root of both sides, you get this. And we get our old buddy plus or minus 1. Okay? So that was, what, step 1. Step 2 is to partition. So we take our...
Why is a duck here?
I don't know why a duck is there. So we take our number line and what? So if we go all the way back to the beginning, don't forget, -1 and 1 were vertical asymptotes. So we would use those anyway. But it seems like we don't have any other critical values for the second derivative, if we're allowed to call them that. So notice I've got this, I've got this, and I've got this, those three intervals. So now what we're going to do is step number 3, we're going to chart. So when we chart, let's see, we are going to have up top, it's going to be 2 and 1 plus 3x squared is the numerator. That's always going to be positive no matter the interval, right? And then the denominator is going to be 1 minus x squared cubed. It's going to be 1 minus x squared, the quantity cubed. And our intervals are from -infinity to -1, -1 to 1, and 1 to infinity, which we just read off of here. So interval 1, interval 2, and interval 3. Okay, so now if we plug in something in this interval, maybe like -11, I think it's pretty clear that that's going to be a negative. So this divided by this is our fraction, and we end up getting that the second derivative will end up being negative. If we put in something like here, 0, always a great choice, we're going to end up getting positive. And then inside here at x is equal to maybe 11, we're going to get negative again. So our second derivative is negative. So that means that f goes from concave down to concave up to concave down. Okay. So now notice those are the intervals of concavity that we could talk about. We could say that f is concave up on -1 to 1, f concave down on 1, negative infinity, -1, 1 to infinity. We do not consider this or this an inflection point because the function is not defined there. It actually has to be a point on the function to be an inflection point, right? But we know that these are vertical asymptotes. Those are both vertical asymptotes, not points. So they cannot be inflection points because they're not even points on the graph.
What is that mouse?
Right. Okay. And then when you put that all together, you get the graph that you see in the key. So I'll let you look at that graph that's in the key. Let me look over here. That's great. Okay. First and second derivative. First and second derivative of this. Okay. So then the nice thing is, what if we don't want to test the fact that you can do a derivative, but we want to give you one already done, a first and second derivative, and see if you can't use that to do that same analysis we just did. Even though that's not easy to read, that is a second derivative here. Make sure you can read that. It kind of squishes together. So if we come over here, so let's imagine you don't even have to take a derivative. Let's say that this is our function, and I give you the first and second derivative. Could you have that same conversation that we just had? Conversation, if I can enunciate. Okay, so let's do some more. So step one would be, let's talk about the domain. So step one, we're going to talk about the domain. Notice what we have. Two things. We either worry about stuff divided by 0, or we worry about the square root of a negative. In this case, it's the square root of negative that we worry about. So we need this to be greater than or equal to 0, which means x is less than or equal to 3. So that means it's either equal to 3 or less than it. So this is our domain. See how that worked? Number 2. So this is part 1, so our part A. So for part B, we're going to talk about the intercepts. And you know that the x-intercept is where y equals 0, and the y-intercept is where x equals 0. X-intercept is where y equals 0. That means you would just take your whole function, set equal to 0. So this is either x equals 0 or this equals 0. So you're going to get this. If you square both sides, get x is equal to 3. So those are our two possible x-intercepts, 0, 0, and 3, 0. Then, if you plug in 0, it should be pretty clear that if you take f of 0, you're going to get 0. Square root of 3 minus 0 is 0, and we get that same value that we had over here. All right. Then for C, we want symmetry. C is symmetry. Again, we take f of negative x. And this time you get negative x, square root of 3 minus negative x. So you get this crap, which notice this does not equal the original, and it does not equal negative the original. So this means no symmetry. Thank you. Are you going to eat one too, please? She's trying to help me and give me some lunch. Take a bite of one of those. Okay, so that's symmetry. Asymptotes. asymptotes, we only worry about rational functions in their asymptotes, right? Either that or you just have one memorized, and I don't think there are any in this case, right? E, so for E, poop, let me see E. Okay, so for E, we're worried about concavity, yes? Wait, let me see. No, I'm sorry, we're worried about increasing, decreasing. So let's worry about E. Let's worry about increasing, decreasing. We know that first we find the critical values. It's going to be step 1, where the derivative equals 0, or the derivative is undefined. Step 2 is going to be to partition. Man, hopefully you know this by now. This step 3 is going to be to chart. We do it the same way every time so that hopefully it sinks in your noggin. So if I take the derivative and set it equal to 0, the derivative they gave me, that's only going to happen if the... so first, I guess I write down, they told me the derivative was this, right? Negative 3x minus 2 over 2, 3 minus x to the 1/2. And two things happen. Either it's where the derivative equals 0, or it's where the derivative is undefined. So derivative equals 0 means what? Negative 3, I'm sorry. It's where the numerator is equal to 0, so it's this. Equals 0 is going to tell me x is equal to 2. And then what? Undefined? Undefined is where the denominator is equal to 0. I think that's pretty clear that that's x is equal to 3, right? So we look at our domain. Well, we already said that it only goes from 3 to the left out to negative infinity, but now we've seen that 3 is a nice critical value, and then so is 2. So that's going to be our step 2, our partitioning. We're going to have this interval and this interval. So that's our partition, and then step 3 is to chart. So when I look at my chart, I'm going to go, well, my first derivative has the following factors. Its numerator is that. Its denominator is 2, 3 minus x to the 1/2. Thanks, kid. Keep on eating. You're doing great. And that is derivative, which tells me about f. So then I look at my intervals. It's from negative infinity to 2, and then 2 to 3 closed. We really only have those intervals, right? So first, I could put in x is equal to negative 100, something really big negative. That's going to give me a negative times a negative is positive. That's always has to be positive if it's going to be defined, because it's a square root. Square root's always positive, right? Unless you were to screw it up with that negative out front. And then over here, if we put in something like x is equal to 2.7, I think you're going to get a negative times a positive, which is negative. So my derivative goes from positive, increasing function, to derivative negative, which means f decreases. So since f prime goes from plus to minus at x is equal to 2, then that implies f has a local max. Right? Good job. So we would say f increasing on negative infinity to 2 and decreasing on 2 to, I would say 2 to 3. Because we really only want to talk about increasing, decreasing on open intervals, so I'm not going to include that endpoint for a very subtle calculus reason. Okay, so let's see. What do we have going on now? One way to think about it is the derivative, when you put in 3, the derivative's not defined. So you would not include that in point 3. That's a main reason why you wouldn't. derivative doesn't even make sense there. So you wouldn't say the function is decreasing at 3. So there you go, kid. Then that's also part F, talking about the local max. And then now let's talk about concavity. So if someone tells us that we want to know about concavity, you know that that's where the second derivative is 0. Step 1 is going to be second derivative 0 or second derivative undefined. Step 2 to talk about concavity is to partition. And by now you better know step 3 is to chart. So if I take the second derivative and they hand it to me actually, and it's this 4, 3 minus x to the 3/2, we know that second derivative is equal to 0, where the numerator is equal to 0. The second derivative is undefined, where the denominator is equal to 0. Numerator equal to 0, I think you should be able to see is x is equal to 4. Denominator equal to 0 is x is equal to 3, right? But notice this 4 is not in our interval. And so what do we do? So that means step 2 is to partition. And partitioning mean we have our number line goes this way. We just have one big interval. Step 3, I don't even think we have to chart, because all we have to do is see that for our second derivative, if you put in anything in there, but if it makes you happy, we just have one interval here, right? And our derivative is 3x minus 4 on top, and on bottom it's 4, 3 minus x to the what? 3/2. So if you put in anything, and I think x equals 0 is a great choice anytime you can, that's going to tell us about this, which tells us about this. If you put in 0, you're going to get a negative, and in here you're going to get a positive. And so the second derivative is negative. That means f is concave down everywhere, right? And that's it. Okay, and again, you can see the picture by looking at the graph that is included in the solution. So I'm going to stop here and come back.